So, let us get started again. Okay, so we will start from where we have left off, sort of listing down all the desirable properties that we had so far, and we will be exploring a little bit more. Mechanism design talks about first listing down all the desirable properties and try to see if we can satisfy those desirable properties in some equilibrium. So, in this list we will add a new one which is called the individual rationality. So, if you just look at the previous properties, this is talking about the DSIC is talking about truthfulness, Pareto optimality is talking about collectively we cannot make all the agents better, and which we also showed is equivalent to allocative efficiency. So, we found a mechanism, in fact a class of mechanisms which are allocatively efficient and therefore Pareto optimal and also DSIC, but there was certain thing that was missing, which was this property of individual rationality. So, what is it saying? The property of individual rationality is saying that why should you even participate. So, sometimes also called the participation constraint. So, if I ever have a situation participation, so if I ever have a situation where I get an object, but I am asked to pay more than I value that object, then it is not rational for me to participate because I might have a negative utility. So, participation constraint is essentially safeguarding you from that. So, if you just look at the definition, the mechanism again f of f and p. So, because we are only dealing with mechanisms with transfers, it is individually rational if your utility, when you are reporting your values truthfully. So, this is always defined with respect to the same type, and the revealed type is also the same. This is going to be non-negative for all the agents. Now, if we have the DSIC property already, we know that people will be in a dominant strategy equilibrium will reveal their true types. So, therefore, nothing to worry that this will eventually get to that theta. All that we need to ensure is that valuation minus payment, this term is non-negative, and we just saw that if I use arbitrary gross payments, then it might not get satisfied always, right. So, if my h I theta minus I function is strange, then possibly we will not be able to satisfy this condition. But for VCG, we know that this and if we are only dealing with goods, so in the combinatorial allocations we are only giving goods. The meaning of goods is that the valuation for such objects are always non-negative. So, the more general definition of goods is that, so suppose I have suppose M is the set of items, and suppose I say that okay, so suppose I have a subset of this set of objects. So, out of all the items I pick some subset, and if I add some item, so let us say S union some item, let us say A, right, minus the Vi of S. So, because in combinatorial setup we cannot really assign a valuation to a specific object, we are always assigning valuations for a bundle of objects. It could be different from the individual items. So, whenever I am adding this item to the existing set S, this should be non-negative. That is what is called a good for I. And similarly, if this number is non-positive, then we are going to call it a bad. Just for your information, we will not use the bads in this case. In fact, you can have the same item. So, this is the good. The same item could be good for one agent and could be bad for some other agent. That is also possible. So, maybe a specific type of item, let us say sugary item, may be very good for a kid. It is a good for a kid, but bad for someone who is let us say diabetic. So, yeah. So, if we are only dealing with allocations of goods, then the VCG mechanism is individually rational is what is the claim. I mean, there is nothing much to prove here, because all that you need to do is to write them down appropriately. we can handle that during the tutorial session. But what I want you to observe is that the VCG mechanism now satisfies all these nice properties, at least these 3. It is truthful in the dominant strategy way, it is Pareto optimal because it is actually doing this allocative efficiency, it is also individually rational for reasonably large class of problems, like when you are allocating goods. Okay. All right. So, yeah, so that was the small remaining part from the previous thing. So, we are actually we have developed the setup of mechanism design. We have looked at different properties, different guarantees that we can satisfy. We saw examples of Groves payments and VCG mechanism, which essentially brings you down to all the different properties, at least in this case, these 3. Let us look at some very specific examples where it is used in practice. So, Google, or I mean, we know that internet advertising is very popular. Whenever you Google for certain stuff, or even if you these days, if you let us say purchase a ticket to Chennai, the next email or the advertisement that you see is hotels for Chennai, right? You might have seen this. Yeah, so what is Google doing is it is actually automatically reading your emails, seeing that you have a ticket from your source to Chennai, and it is already trying to find out that you are actually visiting Chennai between this period of time. So, you must be looking for hotels or staying places. They do not know that the summer school will provide accommodation. So, how are they getting to that? So, and this is different from the traditional advertising, because there are lots of touch points in the internet advertising, because your data is available in some usable form. So, the first thing that why it is very useful or reason for success of internet advertising, and it is everywhere, not only Google does it, your Facebook, all sort of it is very commonly said, right. So, if you are getting anything for free, you are the product. So, they are using your data to essentially sell objects for you, and that is exactly internet advertising is doing. They are doing a good job because they are providing you this service free of cost, but at the same time they are actually crunching on the data. So, when you actually signed up for Google, all that fine prints, that huge document, I agree to all of this, which everyone agrees without reading, that had all these things. I will use your data to external advertisers, they will be bidding for your data, and I will show you ads, you agree to all of them. So, this user data is available when you talk about internet advertising. So, the success is because the advertisers can gather a lot of information from the users in this way and can suggest them products. They can take measurable actions. So, in traditional advertisements, if you think about an advertisement in a newspaper, you are an advertiser, but you do not know how many people have actually seen your advertisement, right. Maybe this many number of copies have been sold of that particular edition of the newspaper, but how many people have actually turned to that page and have seen your ad, that is not measurable. In internet, you can actually do it, because once your ad is shown, and if you see that someone has clicked on it, it is clear that they were interested and they have landed on your web page. So, those kind of measurable actions you can and based on their other information, that what is their age group, what type of so other cookies that they are using. So, maybe during which period of time, is it a rush period like a festival time, they can actually do a lot of customization from. So, this is I am talking from the advertiser's viewpoint, and this is also having a very low latency. People can, so you can actually now employ very clever bidding strategy. So, all these things, very complicated things, VCG mechanism, etc., which was otherwise very difficult to implement in practice. In internet advertising, you can do it, because all that you need is users are putting their real time bids, they can write bots. So, the way it works is that the small advertisers do not have sufficient expertise to do this optimal bidding. So, suppose they want to maximize their revenue, they do not know exactly how to bid, there exists some entity called an ad exchange. So, which actually takes, so which is an interface between, let us say, this publisher's website like Google or Facebook or whatever, and on the other side this the advertisers, and the advertisers can give in simple words that this is the type of audience that I want to engage with, and those ad exchanges put the ads on their behalf to the advertiser's web page, to the publisher's web page. So, a lot of things can be possible. Now, and that brings us to the sponsor search ads. So, I do not have a snapshot here, but if you have searched on, let us say, Amazon or Flipkart or anywhere, you will see that along with, so suppose you have searched for, let us say, shoes, and along with the generic results, which are really the results coming out of some algorithm, they also have some sponsored. So, you will see that there is a small I button there, and it is saying that these are sponsored ads, which is saying that this bidders, if you click on that I button, it will say that how it is using your data in order to invite advertisers. So, those are things that are not part of the generic search algorithm. It is being provided because some people have actually bid for your keywords, shoes, in a certain demography, in certain age group, it will show that particular ad to that agent. So, that is called the sponsored search ads. You are searching and you are getting sponsored search. There are different other types of ads like contextual ads. So, maybe depending on the content of your web page or content of your email, they are sending. So, the other example that I gave, that whenever you purchase a ticket to Chennai, you get contextual ads because people will be looking for hotels or taxis, etc. And this is the most traditional mode of display ads, the hoardings, the usual hoardings, newspaper advertisements, etc. So, those are display ads. Okay. Yeah, so I just talked about the ad exchange. Ads can be complex, the mechanisms could be complex, and therefore, the mechanism that Google works with, which I am sure that will be discussed sometime in this workshop, how these things are actually used. There are lots of algorithmic challenges in terms of how quickly you can do those auction methods and finally show up your ad, because it has to happen with. So, if you search the Google on Google something, you see that the search finished in 0.00002 seconds, right. Within that amount of time, you will have to run your auctions, etc., and finally show those ads to the people. It has to be fast. Okay, so in this example, I will just look at the position auctions and use some of the things that we have already learned, like the VCG mechanism, and how it will actually show up in the payment model of this sponsored search auctions. So, position auctions are the type of auctions that we have just discussed. That if you have, so you can imagine that when you search on Amazon for shoes, the first 2-3 ads, the first 2-3 spots are the most lucrative spots, right. So, people who are looking for for shoes, the first sponsored ad is getting the highest number of eyeballs. So, definitely there is a higher probability of getting a click if you put your ad at that place. So, because those are scarce resource in the setup of an auction, we want to auction, I mean, as an advertiser or as an not as an advertiser, as a publisher, like Amazon wants to auction them off at certain amount of price to the advertisers. Okay, so, to make it kind of consistent with our development of the notation, let us say we have n players. So, now the advertisers are the players, and suppose there are m number of slots. So, we are always going to assume that there is sufficient. So, this is just for our convenience. So, there is at least sufficient amount of slots for the advertisers. All that matters is the ranking, how we ordered them, and yeah. So, 1 is the best position and m is the worst position. Okay. Right. So, historically this position auctions first started I think in the early 1990s or so. They were ads via bid per impression. This is the type of ads we are actually familiar with in newspaper and so on. The moment I show your ad on the banner, I charge you certain fixed amount. Yeah, so just showing the ad, newspaper ads. So what is the downside? If you are a small advertiser, you owe the entire risk, whether it will be seen by someone, whether you will be able to get customers out of these ads, or you earn any revenue. It's completely dependent on you. You will have to make a choice, but they will be charged some fixed price. So, all the risk is on the advertiser and there is no risk from the publisher. What became more popular when I think Google was the first entity which actually brought this pay per click model. Here, so pay per click means that you do not pay just for showing the ad. So, I might show your ad, but you do not pay until someone clicks on your ad. So, once you click on the ad of that sponsored link, then that particular advertiser pays a certain amount of money to the publisher, that is Google, and for a very large period of time. And in fact, I think still today that is the major revenue model for Google. So, to earn money using this pay per click advertising. So, what is different between this bid per impression and pay per click model is that now the risk is being shared also by the publisher, not just the advertiser. Of course, advertiser has to be clever to put the bids in a slightly clever manner, but the publisher gets no money if it shows an irrelevant ad which never gets clicked. So, yeah, so it will be ranked by pay per click. So, yeah, historically it was just ranked by the pay per click. If shown ads are not clicked, the publisher earns nothing. So, this is not a very good idea. Today's approach is like this: advertisers are ranked based on the product of the probability of getting a click and the bid value. So, it is not just based on how many they have bid for. So, in the auction that we have seen, that how much they have bid for. There is also a certain thing called the probability of a click, which we will call the click through rate. We will define that very soon. Okay, so that is the probability of click is called the click through rate. It is a product of these two things. So, in fact, the expected revenue that you can earn if your ad is clicked, based on that it will rank it. Okay. All right. So, to make this model again to yeah.
Can you just skip to the last?
Yeah.
They rank advertiser based on probability of click and the bid value.
Right. So, they bid something, but they also estimate the probability of click. I'll come back to these points. The CTR times the bid value is what they are going to rank it on.
So, there is no sort of reputation clause, like a company which is already very well known is likely to get more clicks.
So that is actually captured in the CTR, which has two components. One is the advertiser component, one is the position component.
Yeah, so the probability of click captures both things, right?
Right, yeah. So the reputation of the company, historically, how many number of ads of a specific shoemaker has been clicked in the past, from that they can estimate it. And also if they are, we will discuss. So this the CTR has two different components, and for simplicity we will assume that they are just products of one another. Okay, so yeah, so the assumption is that clicks generate value to the advertiser, and all clicks are valued equally. I mean, so this is essentially to make sure that we actually come to that model. So let me just get to this model. So the valuation of an advertiser when his ad is shown on the jth position is this click through rate, which is having a component I and j. But the valuation, the once the click has been received, that you have now went to that advertiser's web page, whether you will make that purchase or you will not make the purchase, that is completely independent of this process. So the total value for showing that ith ad in the jth slot is this product. So, it is separable in that way, and once you are in there, so when this CTR actually realizes, then this VI is the valuation that you get. So, we will make further simplification of the CTR, and as Sushmita has already pointed out, that there are two components to it. So, the rho I is the quality component. So, you can think of that this is really a very relevant advertiser for this particular keyword. So, somehow I will have to estimate that. So, someone who I have two different advertisers, let us say I and I prime, depending on who has a higher rho I will possibly prioritize that agent at the same position. And this Pj, notice that Pj is not dependent on the agent at all. It is just so higher position is having a higher probability of getting a click. It is just like I see the first ad first and then the second ad from the viewer's viewpoint, and that effect is captured here. So, Pj is the position component, rho I is the quality component. So, all these are basically to simplify our analysis. So, together you can think of this Vij now as only the position effect and the agent effect. Agent effect takes this rho I times Vi. This is what I want to sort of estimate. Now, what is not known is this Vi. So, if you think about this, we can all observe. So, from our historical data of that agent and how many people have got a click if they are shown on if their ads have been shown on the jth position, we can estimate Pj and also rho I, but we will never know Vi because this is some private information. So, this is exactly where our auction lies. Okay. So, now the rest of the things is sort of quite self-explanatory, that once we have this model of valuation of an advertiser I when his ad has been shown on the jth slot, and we can also assume that this position effect is decreasing with position, which is very obvious to assume that, and we are assuming strict. So, the topmost one, the topmost position is normalized to 1 and everything down below. So, all these things are non-negative, I should have mentioned that. So, these are all non-negative numbers, but Pj is larger than Pj plus 1. So, as you go down, so there are m slots, the Pj's keep on decreasing with the top one being 1. Okay. So, if you are on the top one, at least this position effect is 1. So, yeah, so Vi is the only private information for the advertiser. Pj and rho J's are measurable. So, this is exactly what we want to measure. So, search engines actually estimate, they track each of these advertisers, estimate these rho I's. Pj's are independently estimated because this is not dependent on J, dependent on a specific advertiser. It is how many number of clicks you have got at the jth position. That would be a kind of a very simple estimate. Now, bidders, so Vi is their true valuation and possibly they bid Bi, and the reported agent component therefore is rho I hat, because rho I hat is not being asked by the agent, it is already measured. So, the advertiser is approximating that this component will be rho I hat times Bi, what they have bid. And now, it is very easy that you can actually run this all the slot allocation payments in this position auction using, let us say, VCG. And this is not something that we are cooking up. Essentially, the Facebook ads are placed using VCG mechanism. So, the value of the agent when this particular allocation has happened, now you can think of that AI is the position, right. So, my final allocation is this A1 to AN, and AI is the slot allocated to I. So, maybe AI, so this ith advertisers ad location was, let us say, at the 10th position. So, then that position effect P of 10 will be multiplied, and then this estimated rho I hat and what he has reported, accordingly this valuation will be. So, this is the true valuation. So, if his true type is this will be the valuation, the total valuation when the allocation is A. We will also have to design the payment scheme. So, naturally the efficient allocation will be So if I want to apply VCG, then the first step of VCG is to find the efficient allocation, which is maximizing the sum of the valuations of all the agents. So you collect all the ads, and this is all happening on the fly when someone has someone has entered the keyword and pressed enter. Then all these advertisers or their ad exchange bots are actually running this auction on the fly, allocating this and then ranking it. So what is it going to do, right? So for instance, if I all that we have here, so suppose they have reported theta i's, right? So theta I report or the BI's. So I'll have to maximize the sum of these things of these valuations, assuming that theta i's are replaced with these BI's. They have reported their BI's. How should this A star look like? The allocation of the ads. It's a moment maximization problem, right? So you have the position, so you know that the higher positions have higher weights, and whichever agent maximizes this, I'll place him at the topmost position and followed by the other numbers, right? So I'll sort this out in that decreasing order and allocate them according to it, and that will maximize this this argmax problem. It's fairly simple, I mean computationally very easy. So this allocation is efficient if and only if it's ranked by expected revenue. Yeah.
What does it mean, moment maximizing?
Oh, so essentially we are just doing this stuff, right? So I have a bunch of weights and I have some number of values, let's say call it x. So yeah, so this, I think this comes from the physics thing that, so this is essentially a moment, right? So I have this, so wi's are already fixed. All that I'll have to do is to allocate which xi will maximize this sum. So let's say
We are looking for 0, 1 values for xi.
Well, yeah, so ai, so if I just want to call this row, so I want to place this particular agent at which position, right? So this particular assignment will give me, yeah, so there this wi is already there. So this part is like wi. I know this is agent dependent component. Now the moment, so x, the location that I put this guy's ad is, yeah, is what I have to decide. And where should I add it? So I have a bunch of numbers, and also I know the corresponding weights accordingly. All that I need to do is all these n factorial permutations. Which one should I pick? I'll just I'll sort them in decreasing order and put them in that sequence, and that will maximize this. So this looks like a moment. That's why it's the moment maximization problem. Okay, so that's yeah. That's what we are doing here. So that's the allocation problem. Unlike the combinatorial allocation where you will have to look at all possible combinations, this turns out to be much simpler problem. It's just a sorting problem. Okay, so now the allocation is done. All that you need to do is to payment. So we will have to see how complicated it is to calculate the payment. Now for that we have a recipe. We know VCG mechanism. Just use it. I mean, the efficient allocation computation is not very difficult, so why shouldn't we use that? So for VCG, what are the things that we need to do? So we still have this calculation of some sort of A star, right? So either including that agent, but summing over other agents, or excluding agent altogether, agent I altogether, to calculate the payment for agent I. Right. So just to give you that setup, just erase this up. So our payment of agent I under VCG, theta I, theta minus I, was we first look at the maximizer, over A. So, the allocation set is still, I mean, of course, it has changed because there is one less agent, but the number of slots are still available. So, we look at the valuations of all the agents, the allocation and theta j, and j is not equal to I. So, this is the problem, the solving the maximizing the sum of the valuations excluding agent I altogether. And I also have this the other term where I am looking at the sum of the valuations of all the other agents, but now it is allocatively efficient, and we have already calculated this allocatively efficient outcome in the previous step, right. So, this is excluding agent I and this is including agent I, but summed over all the agents except I, right. So, so let us look at each of these things. So, we already saw this, what will be the allocatively efficient outcome when everybody is present. So, okay. So, let us say they have reported B1 to Bn, and this is exactly like theta I hat what they have reported, right. So, we sometimes we use the hat to denote this is the reported one versus the true one, which is theta I. So, so what will be the efficient allocation in this case when they have reported it? So, just for simplicity assume, I mean this is without loss of generality, I am just renumbering the agents such that this rho 1 hat B1 is larger than at least as much as rho 2 B2. So, these are the names of these agents 1 to n who has this property. So, what will be the efficient allocation then? So, we still have, okay, so we have this all these positions. So, 1 to up to m, and we have assumed that m is at least as large as n. So, there is a space for everyone to be accommodated, just that, yeah. So, we will run out after a certain period of time, and we have also, so from their bits, so we have estimated this one, and from their bits BIs are available, and our efficient allocation is essentially to maximize that moment maximizing function, right. So, this times the P of the position component, that is what we are trying to maximize. So, this one has this P1, P2, and these are in decreasing order, okay. So, how should we allocate what is the efficient allocation here? So, the advertiser 1, because the way we have defined it, advertiser 2, 3 and up to n, right. This is the efficient allocation. Okay. So, that is allocation is this. Now, I will also have to calculate what is the payment, right. Yeah. So, I am just using one small notation just to look at the first component, but if you think about this first component, what should happen? So, suppose I want to find the payment of this third agent here, right. So, let us say the payment of 3. Using VCG, what should happen here? So, the first term is actually calculating removing this agent altogether. You still have this m positions, but you do not have third agent anymore. So, in fact, you are plucking one of these guys. So, the order still remains the same. What happens in the allocation? What is the efficient allocation in that case? Everything gets shifted. Yeah. So, all this 4 to n, they are stepped up in one position. Okay. So, that is the let us say A star minus I, right. So, that is what I have denoted. And if you look at this quantity where the agent was present, let us say 3 was present, but some of the values excluding this agent. So, I am looking at the valuations of all the other agents. What should be that quantity? I mean, I think you can work out these two differences. So, are there some common terms which will get cancelled? The top part will get chopped off, right. So, yeah, so you can think of that. Yeah, so when you have this PI VCG, so this is this part, the first component, and this is the second part where A star is also including agent I. You see that starting from, so I am starting from I up to n minus 1. So, okay, so I think I have numbered it differently. Yeah, so here these are j plus 1, so that is why it is I. So, therefore, you will start from the j plus 1. Your position is still remaining the same. So, this is P 3, but you are the fourth agent has now moved to the third position, fifth agent to the fourth position, and so on. So, this is that one, and when it was present, everybody was shifted down by that. So, all that has changed is, so starting from 1 to I, those agents have been removed because they are on the both sides, they cancel out. Only the remaining part, they have moved by one position. So, now you can do the simplification, you just have this part, and the difference between this the position component is essentially the amount of payment, this part. Okay. And you can see that the last agent who is at the bottommost position, even though he gets, so okay, so he pays nothing because there is nothing. So that is why this is from I to n minus 1, this is for all the agents up to 1 to n minus 1, the last agent pays nothing. Okay, so this is a very simple way, and because it's the expected payment that we are thinking about, because everything is being multiplied by the probabilities. So, for every click you are going to charge this much amount, which is when you take the expectation, it will just become the PI VCG. So, every time you click on the on a Facebook app or Facebook ad, the advertiser pays Facebook this much amount of money. Okay. All right, so that's a kind of a yeah, just an example of how this is actually used in practice. Maybe the actual implementation is Facebook is slightly different, but you see the point that how we can actually use, and because this is the VCG mechanism is truthful, everybody has incentive to report their evaluations, the bids truthfully. Okay, so before we close, of course, this VCG mechanism has a lot of good things, in fact all these three properties, but it is it's good to know where you can apply VCG, where you cannot apply VCG, right? Yeah.
Sir, like in this model, if the company is more reputed, they can get, like they can publish, like they can put ads by paying less amount. But as publisher, I want more reputed companies to pay more. Like
not really. It's the expected revenue, right? So, in a pay-per-click model, you don't earn anything. So, your bids could be lower, yet your conversion will be very high, right? So, you are selling, so you are placing the ad for, let's say, for shoes for Adidas. You know that the Adidas click will always happen. Then you learn this, then you earn this money. Some XYZ companies ad, maybe they are bidding higher, their reputation is so low that even if you have wasted that real estate in your website, but that never got clicked, you earned nothing. So, it's an expected revenue maximization thing, right?
Why does, like Google, why would they care about all these properties? Like these properties, the advertisers would care about it.
That's the pay-per impression model, right? So, you can straight away put a banner ad, right? So, think about a small advertiser. So, why it is popular? Because now everybody uses this pay-per-click model. The security that they have is this: Google is already doing a lot of data mining on my data and showing me only when I have a very high chance of getting a click.
What I'm asking is, like, does VCG also maximize payment or something?
No, it does not. I mean, that is a topic for tomorrow. How we can actually sell this kind of a slot so that so as to maximize the revenue.
If there is some other mechanism of such kind, then why would Google use this?
So that I don't know, that Facebook has to. Okay, so the problem here is the revenue maximization problem. I think this will be also discussed in Shushmita's tutorial. The thing is that this kind of a solution, so what we are going to discuss tomorrow is about selling a single indivisible item. There we know how to maximize the revenue. The problem for selling 2 items is still not solved an optimal way. So, people have tried various types of hacks, maybe a kind of an approximations. So, because the problem does not have a clean answer, different companies apply different types of techniques. So, yeah, so VCG is sort of not a bad mechanism, but it does not, it's not provably the revenue maximizer. For single item auction, yes, the second price auction. So, we will see that a variant of second price auction will maximize the revenue. Yeah, so I mean, I do not know exactly why Facebook uses this. So, okay, so so any other questions before we move?
Can I just add that
Yeah.
part of it might be it's fairly simple. So obviously Facebook is able to use it. So that's it is implementable, the system, and the market agrees that this is a good, it has good guarantees.
Right.
Therefore, people buy into the system. So it becomes self-reinforcing when more people, advertisers are going to sign up. So all these guarantees actually incentivizes or motivates people to show sort of advertise on Facebook.
Maybe that's true.
Right?
I mean,
This click per view thing where you only get charged if somebody clicks on your ad basically tells the advertiser that Google is trying its best to generate clicks for you.
yes,
Now, if people buy or not buy, that is a very much more complex. That's a sales
Yeah.
question, marketing question.
Right.
They go to your website does not work in Google.
yeah,
Right?
Yeah.
But at least the fact that it's being clicked shows some kind of intent from the
Right.
side of the user.
yeah. And I only charge you when you when the user is showing intent of purchasing or
Yes,
going
which
to
is
your.
the click.
Yeah. So sharing the risk. So because an ad or clicking an ad, seeing an ad is a stochastic process. So who will take the risk of this particular transaction happening? That is being shared by the publisher as well as the advertiser. While in the paper impression, like this banner ads and the newspaper ads, it's completely on the advertiser. So bids also do some price discovery, right? So that is also another thing. So if you have to sell it, let's say this usual huge banners, there you have a fixed price. You cannot really charge people money more if there are higher bidders. So this particular slot, whoever qualifies, whoever comes first with that price tag, I'll sell the item. So this is like an item which is for which you know the distribution. So yeah, so roughly the intuition is that when you know the distribution of valuation among agents, then you can set a fixed price, take it or leave it. If you do not know agents' valuations, you do this price discovery using auctions, right? So that's the intuition why, and yeah, so the auctions mechanisms are trying to discover that. Okay, so the pros and cons of VCG, of course, we will discuss about the limitations where VCG has some serious downsides, but first let us look at the good things about VCG. So the first thing is it's truthful, and what DSIC truthful gives you is a very low cognitive load. So if you are a small advertiser, if you know that the mechanism is not truthful, then you will have to find out what is the optimal lying policy, right? That could be very highly cognitive for the small bidders. Maybe some bigger bidders will be able to figure out, and that creates a kind of a confusion. Maybe I will not participate at all. DSIC makes that problem clear. You know your valuation truth. I mean, you perfectly know your own valuation. The best thing that you can do is to reveal it. So, and it also, we have seen, it does not give any subsidy. So the VCG mechanism, of course, under certain conditions. So it does not have any deficits. So you can always earn money. You'll never have to subsidize them. It also, we did not prove it explicitly, but it's very easy to prove that you never charge an agent who gets no items. If you are not shown in the in this advertising, if the number of advertising slots were less, then you will definitely not be charged. So individually rational, you will never be. Yeah, so that's essentially leading to the next point, that it is also whatever you bid, you will never be actually charged more than that. So, you will never lose money. All right. So, with all these good properties, it is very sort of motivating to use VCG mechanism. Let us look at some of the limitations. So, and this first kind of concern or criticism is not necessarily for VCG, it is true for any truthful mechanism which requires full information from the players, right. So, it is actually asking, it is revealing true valuations by all the agents. So, think about two companies who are competing against each other. So, let us say Tata and Reliance does not want them each other to know that how much they really valued this spectrum, right. Is something that their company trade secret. So, could there be a little bit more private mechanism, and there is a thread of research which talks about how you can do these transactions, but in a little private manner, not the VCG way. Transparency is another question where you are actually questioning the mechanism designer. So, here we are always assuming that the mechanism designer is actually doing what it is supposed to do, like it is trying to do this allocative efficiency and all these things, and then charging the payments, and it is not introducing, it is not doing some malicious activities. So, imagine a situation where suppose, so we are running a second prize auction and there is only one thing to give out. So, the highest bidder is 1 million rupees, 1 crore rupees, and the second highest bidder is 10,000 rupees, right. So, your second prize auction will earn a very less revenue, right. So, 10,000 rupees where the value to at least one of the buyers was 1 crore. What an auctioneer can do in order to earn more revenue is to introduce some fake bidders. If it somehow finds out that, okay, so this particular buyer is very highly valuable, he might buy it for 1 crore. So, let us introduce some 50 lakhs fake buyer, fake bidder, he will never win, but it will actually jack up the payments that is being paid by the highest bidder. Right. So, those kind of things, that transparency, so if you do not trust the mechanism designer, then those kind of things are not completely solvable. Okay, so that is I mean, this is not specific to VCG, it is for any type of mechanism which is using this type of a thing, mechanism design without mechanism.
Is there any way to tackle this issue?
So, there had been some attempts to do so in the world of okay, so I know one thread of research which is under this. So, if you Google for mechanism design without a mechanism designer, so I think there is a thread of research papers, but they were all pretty old, like 2003, 2005, around that time. So, this question is a real question, that how can I actually, if I do not trust the auctioneer, how can I still run the VCG mechanism in a decentralized manner. So, this decentralized mechanism design, I do not know what is the current state, but there had been some efforts. Yeah, so in the modern days, people try to do this blockchain kind of a technique where you can actually verify these transactions. So, what you are actually saying that this is really the second prize, even without having an auctioneer, you can verify that there was this second prize which is available somewhere, but you do not know the identity, nor you know who has bid for that, but you can verify that this is the second highest bid. Yeah.
For the first point, I think people in cryptography use multi-party computation.
Right, and also there is so this differential privacy type of thing, that how much information is revealed to everyone. So, if you change your valuation very largely, the effective change in the outcome will be very small. So, you have sort of a, so you will be guessing over a very large space of valuations. Yeah, so secure multi-party computation is one way of taking care of the first thing.
It's like a zero knowledge proof, right? You don't reveal the identity, you just reveal that there's some.
Yeah. So, I do not know the literature which actually handles this, but yeah, so it will be interesting to.
There is a field in cryptography specifically in for dealing with elections and auctions, I think.
Okay.
Most of the papers are by Ron Rivest, and now it has been taken over by ETH Zurich, a research group in ETH Zurich. So
Okay.
they actually work on the
So
allied fields of
even in the
elections and auctions.
elections and auctions, but not in general mechanism design
No,
or
no, no.
mechanism with money. Okay, yeah, so it will be interesting to take a look at those research, but yeah, so I do not know, I don't have a conclusive answer. So this is a kind of a limitation of mechanism, not necessarily VCG, any mechanism which is assuming that there exists a kind of a trusted entity which is a mechanism designer. All these results are dependent on that there exists a mechanism designer who is doing the right thing, who is running all this allocation, payment, everything. The second thing, I think this also came up yesterday in some discussion, that what if two agents for their own benefit actually collude with each other. So, let us say there are two bidders. Okay, so in this case there is a public good decision. So, A and B is like this bridge or something, and the third column is the payment that they make. So, if you apply VCG, you will have to pick the one that maximizes the welfare or the sum of the valuations. So, in this case what will be picked? So, forget about this third column. So, A maximizes the sum of the values, right. So, if A is picked 300, if B is picked 250. So, if you so what will be the VCG payment for agent 1? So, the first component is you remove that, calculate it, it will be so the first component in that payment term is 250, and if you include that agent, that is the outcome is A, the sum of the valuation of the other agents is 100. So, 250 minus 100 is 150, that is the payment that 1 will make. Similarly, you can calculate for 2 and 3. 3 is not a pivotal agent, so therefore, VCG will not charge anything to them. Okay. Now, suppose agent 1 and 2 decide that, okay, so we are anyway getting what we are deciding A, the outcome does not change. Let us increase our payment, increase our valuation report. So, it will not work. So, because VCG is truthful, it will not work if exactly one agent changes its valuation. We have already proved it. If everybody else is still playing whatever they were playing, then any individual deviation will not be beneficial. But what happens here is that they misreport together to a higher value. Now, if you calculate, so now what changes it makes is that it makes even the agent 2 a non-pivotal agent. So, now this agent, even without 2, you have A and B, I mean they are tied, no matter whichever you pick, A or B, it still has the same valuation. So, the first term is still the same. The second term for player 2 is again 250. So, therefore, it cancels out, it pays nothing, and also the payment reduces for player 1. So, still they get the same outcome. So, their true valuation is still 200, but they pay less. So, therefore, both of them are actually getting better off. So, VCG mechanism is not collusion proof. So, if more than one agent can actually create a cluster or create a so it is protected against individual deviation, but it is not protected against group deviation.
Is it coming from normalization? Would it work even if it is normalized?
Normalized meaning the
sum is constant. Like here, it looks like because of that 1 is richer than 2. This is happening. If we allow everyone,
the sum of these valuations for these two items is the same.
yes.
I do not have an example right away, but I do not think that will make a lot of difference. I will have to think about that, but I mean this is not a artificial scenario. I mean people do have higher valuation than other people in the cardinal setting, even without normalization. So, if we do the normalization,
It will just scale the numbers. If you
no. So, what he is saying is that, so 250 here also you will have to add these two things to 250, here also you will have to add these things to 250. So, then yeah.
While I'm increasing my valuation for the A group, nothing stopping me from decreasing my valuation for or B good,
B good,
and
yeah.
still keep adding up to the same value.
Yeah, so if you are assuming, right, so if both positive and negatives, yeah, I think that's I think will be, okay, so just have to think through it that, so originally we also had, let's say 200, so let's say everything is 250, so this is 200, I'll also have to have 50, but then
And
B
B
will,
to 2, and then keep B to 0.
huh?
So yeah, that was 200 and B was 50. So after increasing A to 2,
No. So I'll also have to make 2. So the example has to be reworked, right? So this has to be again increased to a certain value. Let's say this has to be 250 and this is 0, right? Now what is the payment in that case? Just have to work it out. Can someone, yeah, so can maybe in the tutorial session remember this example. We'll do it. But even without that, I think it's plausible that people can actually do a group deviation and both can get better off. So it's not it is susceptible to collusion. So the third point is that so there is no limitation, and of course here we are not using normalization at all. So payment actually could be very large. And why is this true? So let's look at this specific example where the objective is that you will have a item delivery, so you will have to find the shortest path, or I mean all these things are costs and they are additive. So I'll have to go from A to F in the minimum cost way. So this is the cost version. So you can think about the valuations as the negative of these numbers. Right? The source is A and destination is F. So what is the shortest path here? ABEF. So if I just want to find the valuation, the payment, okay, so we will just consider these two cases when the AC path has a cost of 2 versus when it increases to 8. Okay, so each age is a player now. The efficient allocation is, as you said, ABEF. The payment that so each of these ages are agents now. So I am just thinking about how, so this is the cost setup. So every agent should get paid now. You are using their delivery network, then you will be paying them. So how much payment should this agent AB, that age AB will get under this VCG mechanism? So you think about this, that the first term is when that agent is not present, right? So you will have to, so the first component is this age AB is not present, in which case you have this path, and then the shortest path will be ACEF, right? I think that's the shortest path without AB being present. So that has a cost of -2, -3, -1, and in the efficient allocation, that is the second term there, what is the sum of the valuation of all the other agents? Of course, you are not using this path, so their valuations are 0. So only the ages that you are using is 1 and 1, -1 and -1. So you are getting paid an amount of 4. So the mechanism designer has to pay this 4 amount of money to agent AB. Now this cost has increased to 8. I mean, nothing has happened in the shortest path. So somebody else has increased its cost. So the only difference that it will have is that the first term, except AB, the first term will get greatly increased, right? So you have no other choice but to go to A to C, and you incur this cost, and you can increase this number arbitrarily. If the path becomes costlier and costlier, it is the threat that if you remove AB, you will have to take a very high cost. So that is making this the payment made to AB to be very large. So you are now paying 10, and there is no limit that you can put here. The more expensive this AC path becomes, the higher payment you will have to make to the agent AB, which is on the shortest path. So this is actually a kind of a problem, and of course VCG. So there are some works which, so of course, VCG is not the one solution pill to every problem in this world. So, in the network world possibly there exist better mechanisms which maybe satisfies a certain different type of objectives, yet it gives a little better payment scheme. So, yeah, so for instance, if you think about a very simple setup, so yeah, so very similar to this problem. So, suppose I have a single, let us say, indivisible item to sell, and I have a path graph, and all the intermediate nodes have no values for this item. So, their values are zeros. But if this agent does not forward this information, then you will never get to sell to this last agent. Let us say he has a very high valuation, right. So, you can do this VCG. So, this is the seller. So, let us say a seller is selling one indivisible object, and if you just want to maximize the social welfare, you will be always selling it to the last agent, but you will have to make a payment of let us say minus 100, right. If this agent is not there, then you make no, so the transaction does not happen because there is nobody who can purchase it for any positive values. So, the first term will always be 0, and the next term will be when this agent is present, what is the sum of the valuation of the other agent. So, that is 100. So, you are paying everybody minus 100. So, you are actually getting 100 rupees, but you are paying maybe many rupees. So, VCG is not the, so in such kind of scenarios there are works in network auctions which can actually do something better. So, that is not in the scope of this tutorial, but of course, there exist mechanisms. So, that is to say that VCG is not the end of the story. There exist other mechanisms for specific problems like graphs. And this is a very interesting example. If I see that, okay, so I had some revenue being generated when I had, let us say, 20 people, and now if I have 100 people, I should expect to gain more revenue, right. So, my payment should be at least as large as the previous one, if not more. But that revenue monotonicity does not hold for VCG, and here is the reason. So, suppose initially I did not have this third agent, right. Now, you know that VCG will allocate, so take this public decision of f, and it will charge the second. So, this is a very simple second price kind of a scenario. If you remove that agent, you get m, which is the first term, and if you include that agent, then the other agent gets 0. So, 90 minus 0, this guy will pay 90, and this is not a pivotal agent. So, therefore, this agent. So, the things in black is the original setup. We had only 2 players. When the third agent enters, it also has a value, high value for this outcome f. Now, suddenly by including this agent, now you see that no agent is pivotal, right. So, you remove this agent, f becomes the outcome. You remove this agent, still f is the outcome. You remove 1, still f is the outcome. So, none of the agents are pivotal, and because of, I mean, you can do the calculation, but VCG will never charge any payment to any of these agents. So, your revenue has actually dropped from 90 to 0 because one new agent has joined. So, this is actually violating the revenue monotonicity, which is also not a very desirable property. Right, and so we have not discussed this property called budget balanced. You can think of that the payment that we are collecting. So, all this, if you look at all the VCG payments for all theta I, theta minus I, I think we have discussed in the very beginning what is budget balance, but let me just try to remind you. So, if I take the sum over all the agents and take the total payment, if this is exactly equal to 0, then it is called budget balanced. The interpretation is that you are not generating revenue or subsidizing the mechanism, rather you are just redistributing the payment among different agents. So, somebody is paying. So, this means that there are some terms which are positive, some terms which are negative. On aggregate, this is summing to 0. So, somebody is paying, somebody is consuming that payment, and therefore, the mechanism designer is happy that it is not doing any revenue extraction. So, it is possibly reasonable for, let us say, from the viewpoint of a government does not want to generate revenue by redistributing items or doing this auction. It just wants to redistribute the revenue, the utilities in a certain way. The sum of the payments should be exactly equal to 0. But this property is not necessarily true for VCG. For certain cases, of course, in the auction, the single item auction case, you have seen that there will be some amount of revenue generated, the second prize value, and the auctioneer just takes that away. But it is not redistributing to the other players, because if you redistribute, then you break the truthfulness guarantee, right. So, in order to do that, ensure that truthfulness, what is known as this money which is being generated is to be burnt. So, there is a terminology called money burning, and money burning is a, so from the current setup, as if this amount of money has been burnt. So, nobody has accounting for it, money is generated from the bidders, and that money has to be destroyed before you get into the next mechanism. You cannot redistribute to the same agents. So, actually, right. So, this is the money burning problem. So, we have actually done a work. If you are interested, you can take a look at this paper of ours, which talks about. So, there is a famous result which says that efficiency and budget balance cannot be satisfied together. So, we give a result where how much we can burn and what efficiency we can compromise. So, it is actually saying that in, so if you aim for an, so if you always have a budget balance mechanism and also of course truthful mechanism, then you have a special structure of the mechanism and you can minimize the efficiency, and to what extent you can minimize. So, minimize the inefficiency or get as close as possible to the efficient outcome. So, we know that efficiency and budget balance with truthfulness cannot be satisfied, but we can have the truthfulness and budget balance property and inefficiency to the minimum possible extent. Okay. So, yeah, so the final takeaway message is to essentially not to say that VCG is not useful. It is certainly useful, it is useful in various settings, but you should know certain limitations which through which you can use VCG more effectively. Particularly for this graph type of problems, VCG is not the best mechanism to do, mechanism to use. But yeah, so for sponsor search auctions and cases where combinatorial allocations, VCG or VCG like mechanisms are pretty popular. It sort of gave us a kind of a launch pad from which we can design other type of mechanisms. This idea of marginal contribution, the agent when it is present versus when it is not present, this idea is used even in various other contexts. We will see in the cooperative game theory a very similar idea of the marginal contribution. Okay, so that's it for today. So, we will take a break.